So hi everyone, in this video, I am going to introduce you the concept of graphs. So we are going to discuss some basic terminologies that are related to graphs, and then we will also show you some applications of graph modeling, and later we will delve deeper into the topic of directed versus the undirected graphs, as well as theorems that are associated with these topics. Okay, let us start by defining a graph. So a graph, denoted as G of V and E, consists of non-empty set V of vertices or nodes. So you can see here a set of vertices A, B, C, D, and E. So not just the set of vertices, but a graph also consists of set E of edges. So as you can see here, there is an edge between A and B, with B with itself, B and E, E and C, D and E, D and B, and then D and A. So an edge, as you have seen, is said to connect the two vertices or nodes. So for example, this D and E is connected by an edge. We can then say that this edge is incident to D and also incident to E. And we can also say that D is adjacent to E. Likewise, E is adjacent to B. So let's say that the definition of an edge is that it connects vertices or nodes. So we can then say that since D is also connected to B and then A, so we can say that D is adjacent to E, to B, and then to A. So, and if we look at E, E is adjacent to C, to B, as well as D. Okay, so an edge may also connect a vertex to itself. So as you can see here, this edge has only one vertex and it connects B to itself. So this is called a loop. So we can then say that the edge may connect one or two vertices. All right. So now let us move on into the basic types of graphs. So one type of graph is the undirected graph, in which this graph has no directions. And we can also call it as a two-way path. So as you can see here, there is an edge between A and B, means that there is a way or a path between A and B. And likewise, there is also a connection between B and A. There's a connection between A to D and D to A, D to E, E to D, D to B, B to D, and so on and so forth. Okay. Meanwhile, if we have a directed graph, it is a graph with no directions. In this case, we consider this as a one-way path. So as you can see here, compared to here, which has a two-way path between A to B, and here we specify that there is a path only from A to B, but not B to A. So likewise, there is a path between A to D, but not D to A. So we specify here the direction. Okay. So this is the difference between the two. In the undirected graph, it's just a graph without directions, and we can consider it as two-way path. But for the undirected graph, it is a graph with directions. Okay. And here are some more terminologies. We have a simple graph. So what is a simple graph? So shown here is a simple graph, but why can we consider it as a simple graph? Okay, I've said simple graph so many times already. Okay, so it's simply a graph that does not contain multiple edges or loops. Okay, as you can see here, we have a distinct edge in between vertices. Okay, so each edge connects two distinct vertices, and there can be at most one edge between any two vertices. So for example, this vertex and this vertex has only one edge, and this vertex and this vertex is only one edge, and it's similar for the rest of the vertices and for the rest of the edges. Okay, But what about for the multigraph? So a multigraph, on the other hand, is a graph that allows multiple edges between the same pair of vertices. So if we go back here, we have one distinct edge between these two vertices. But in a multigraph, it allows multiple edges between the same pair of vertices. So meanwhile, if we have a multigraph, this is a multigraph. So in other words, it is just a graph that allows multiple edges and also loops, then we call it as a pseudograph. So basically, a pseudograph is just a multigraph with loops. So going back, this is a simple graph. So distinct or one edge, at most one edge between two vertices. But in a multigraph, there may be multiple edges between the same pair of vertices. And a pseudograph is just a multigraph with loops, okay? Or a pseudograph is just a simple graph plus the multiple edges plus the loops, okay? Now, these are just the simplified or we put all the graphs in one page so we can see the differences. All right. Now let's move on to the application of graphs. So graphs and graph theory can be used to model computer networks, social networks, communication networks, information networks, software design, transportation networks, as well as biological networks. So in your journey in computer science, so in what specific application have you used the graph? So one example would be when you were tasked to create, let's say, flowcharts, right? So you can see how one line of code is related to another line of code, or one task is related to another task. Anyway, moving on. So we have the computer networks, and we can use the graph to model this networking. So we can represent routers as well as the different sites that are connected to specific router using nodes. So as you can see here, we have nodes or routers A, router B, router E, C, and D, and the internet router. And we can also represent the sites with a node. So in other words, these sites are containing computers that are connected to a certain router. So for example, we can see here an edge between router A and site A. So basically, we are just saying that these computers are connected to router A. And we can also see a connection between router A and router B. So we can say that router A and router B are connected. Okay? And we can also use graph modeling to represent social networks. So we can use the vertices to represent individuals or organizations, and the edges to represent the relationships between them. So for example, this is a social networking site, and these users that are connected to this are basically those who are using the social media network. But in this case, this user simply viewed the social media site or networking site, and the rest of the users are have actually accounts. Okay, and we can also model the relationship in between users. So for example, these two users are following each other on this social media site. Okay, and we can also model the activities of certain users. Let's say this user has posted, and this certain user, on the other hand, has liked and comment the post that was posted by this other user. Okay, and we can also use graph modeling for making influence graphs. So influence graphs are just a way to look at the factors that are involved in making a certain decision. So for example, you have a socio-economic status na factor, and based on the socio-economic na factor, can we correlate it with a person's probability of smoking. And if that person is smoking, then what is the risk of that person for getting a lung cancer? Okay, or let's say if based on the economic na status, what would be the probability that a person would be exposed to asbestos? And since that person is exposed to asbestos, what would be the risk that that person will get a lung cancer? And so on and so forth. So here's another example. Suppose we are modeling how we approach solving a certain problem. So first you ask, what is the situation? And based on the situation, what would be our solution? And based on our solution, what would be a certain outcome? Or based on the situation, what would be the outcome? Or that based on the solution, how 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 do we like the solution that is being proposed? Okay, and we can also use graph modeling to model collaboration. So here's an example of an academic na collaboration. So this represents or models the collaboration of researchers who have jointly written a paper in some subject. Okay, so let's say this Diego Lopez de Opinia. So the vertices here or the nodes represent the certain researchers. Okay, and if the two researchers are connected, it means that the two researchers have collaborated in writing a paper. Okay, so we can see here that Diego Lopez de Opinia has written a lot of papers, and he is connected to a lot of researchers like Unai Aguilera or Pablo Orduña, or let's say Jonathan Ruiz de Garibay. And it basically means that Diego has collaborated with these researchers in writing a paper. Okay, and we can see here Gorka Ascune. So we are basically saying that Gorka has only collaborated with one researcher, which is Diego. Okay, and we can also model the citation network. So the research papers in particular are represented by the vertices. So this paper is written by Song, this paper is written by Westphal, this one by Kauri, and so on and so forth. So they are also sorted by chronological order from the least recent to the most recent. So when a paper cites a second paper as a reference, there is an edge from the vertex representing this paper to the vertex representing the second paper. Okay, so we can see here the most, let's say the recent na published papers. So since they are just published papers, so the tendency is there is no citation yet. Okay, so let's say that this paper by Crandall has, we can see that it is connected to Rubio. So meaning the basis of Crandall in making his research or writing the paper is Rubio, in which Rubio based his paper from Goyat or from Wolf or from Kleinman and so on and so forth. And we can see that it is Song that has actually started the research and is the foundation of all these researches. Okay, so we can also use graph modeling to model graph theory to model the airline networks, and we can represent the airports by vertices. So each flight will be represented by a directed edge from the vertex representing the departure airport to the vertex representing the destination airport. So for instance, if you wanted to travel from this place to this place, so you can see that there is a flight in between these two places. Okay, and we can also model the road networks wherein the vertices we can represent the intersections and the edges will be representing the roads. So we can see here a top view of a certain place, and we can simplify that using graph na models. So we can get all the intersections, and if there is intersections and if there is a certain road between two intersections, then we can represent that with a graph. And we can also use undirected graph to represent two-way na roads, meaning let's say this is a you can go from this place to this place and from this place to this place. But if it is only a one-way na road, we can use a directed na directed na edge. All right. And we can also model biological networks. So for example, we can model the protein interaction or protein metabolites na interactions. Okay. Yeah. So there are a lot more of applications of graphs, and they are all not mentioned in this presentation, but you can do more research on it. Okay. Yeah, in the next topic, we are going to discuss about the undirected na graphs.